Hello everyone, today I am going to start with the topic vapor pressure of liquid solution, vapor pressure of solution of solids in liquids. So let us first start with the topic vapor pressure. Let me start with the definition of vapor pressure. Now vapor pressure of a liquid may be defined as the pressure exerted by the vapors above the liquid surface in equilibrium with the liquid phase at a given temperature. So vapor pressure of a liquid means the pressure that is exerted by the vapor on the surface of the liquid, which is in equilibrium with the liquid phase at a particular temperature. Now that means if we place a liquid in a closed vessel, the vapors from the liquid, when the liquid evaporates, the vapor from the liquid cannot escape as the vessel is closed, so it will exert some pressure on the surface of the liquid, and this pressure is known as the vapor pressure. Now vapor pressure of a liquid depends on the following factors. Number one, nature of the liquid. Liquid having weak intermolecular forces are more volatile, that means more vapor pressure. For example, if we choose water, or if we compare water with vapor pressure of water with the vapor pressure of diethyl ether. So as we know that in water the intermolecular forces of interaction present is hydrogen bonding, which is stronger enough in comparison with the intermolecular forces present in diethyl ether. So as intermolecular forces of interaction in water is more, so escaping tendency of water vapor from the liquid surface is less in comparison to ether. So ether evaporation or ether vapor formation or tendency more hobo as the intermolecular forces is less. So ether is more volatile in comparison to water. That means vapor pressure of ether higher than vapor pressure of water. Another factor is your temperature. Now vapor pressure of a liquid increases with rise in temperature. So vapor pressure increase or temperature increase. This is because with the increase in temperature, the kinetic energy of the molecules increases. So as the kinetic energy increases, the tendency of the molecule to escape from the liquid surface increases. So vapor pressure increases. So temperature increase koile molecular kinetic energy increase. So as the kinetic energy increases, so more is the kinetic energy, large number of molecules now tends to escape from the surface of the liquid, as a result of which vapor pressure increases. So as the temperature increases, vapor pressure of the liquid increases. Next is vapor pressure of liquid solution. So vapor pressure of liquid solution, two component system, both are liquids. So the vapor pressure of liquid solution, quantitative relation explained, that is the quantitative relation of this vapor pressure in liquid solution is explained by Raoult. So Raoult law, according to Raoult's law, it states that for a solution of volatile liquids, the partial pressure of each component directly proportional to its mole fraction. So here it is two component, both the components are liquid. So let us consider two component A and B. So according to Raoult's law, the vapor pressure of component A is directly proportional to mole fraction of component A. So if we remove this proportionality symbol, so we have to use a proportionality constant. So PA is equal to PA naught XA. Similarly, PB is equal to proportional to XB. So PB is equal to PB naught XB. Now this PA naught and PB naught, PA naught, PB naught is they are the vapor pressure of the component A in pure state. তার মানে before mixing, when component A is present alone, then the vapor pressure of component A or vapor pressure of the liquid A is represented by PA naught, and PA is the vapor pressure of the liquid when we mix the two component or two liquid A and B. Similarly, PB naught is the vapor pressure of the component B alone, and PB is the vapor pressure of component B in solution. So PA, PB are the partial pressure and XA, XP are the mole fraction, and PA naught, PB naught are the vapor pressure of the pure component A and B. Now, if P total is the total vapor pressure, or we can write simply P is the total vapor pressure, then according to Dalton's law of partial pressure, P total is equal to PA plus PB. That is P total, that is partial pressure of the solution is due to the partial pressure of component A and component B. Now again, from Raoult's law we know that PA is equal to PA naught XA, PB is equal to PA naught XP. Now if we replace this mole fraction XA by XP, because we know XA plus XP is equal to 1, so XA is equal to 1 minus XP. So PA naught 1 minus XP plus PB naught XP. So PA naught minus PA naught XP, PB naught XP. So PA naught plus PB naught minus PA naught XP. XP আমি common লৈ লৈছোঁ. So now you can see from this P total is equal to PB naught minus PA naught XP plus PA naught. This is like your straight line equation. Now if we draw a curve, pressure versus mole fraction, pressure versus mole fraction of the component B, then we will get a straight line, y is equal to mx plus c. So we can say that PA naught and PB naught, they are the constant at a particular temperature, because PA naught and PB naught are the vapor pressure of component A and B in their pure state. So they are the constant at a given temperature. So we can say that total vapor pressure varies linearly with the mole fraction XP, or if we replace here XP by XA, then we can say total vapor pressure varies linearly with mole fraction of XA. Okay, so আমি যদি এইটো গ্ৰাফিক্যালি ৰিপ্ৰেজেণ্ট কৰোঁ, তেতিয়াহ'লে so আমি এটা গ্ৰাফ যদি ড্ৰ কৰোঁ, vapor pressure versus mole fraction x axis, vapor pressure y axis, and দুটা n consider কৰিছোঁ. Now this here XA mole fraction of component A is 1, so obviously mole fraction of component B is 0 hobo, because summation of mole fraction is 1. So here only pure component A is present. Here XA is 0, XB is 1. That means only pure component B is present. So mole fraction of A increases from right to left, mole fraction of B increases from left to right. Now এতিয়া যদি আমি এটা গ্ৰাফ ড্ৰ কৰোঁ, PA is equal to PA naught XA. So this is according to Raoult's law. So pressure or partial pressure of A is equal to partial pressure of pure component A into XA. So this equation is y is equal to mx. So it is a straight line equation. So y is equal to mx. So it passes through the origin. Y is equal to mx. Okay, origin through the pass hole. And if XA value is 0, here it is 0, no? So if XA is 0, XA 0 hole PA is 0. So when XA is 0, PA vapor pressure is 0. Now as XA increases, and when it is XA is maximum, it is 1. When XA is maximum, it is 1, then PA is equal to PA naught, that is this point. XA is 1 maximum point. So PA vapor pressure of component A will be maximum, it is PA naught. Similarly, if we draw a graph, PB is equal to PB naught XP, then again a straight line passing through this origin, and y is equal to mx palu, and if xp, when xp is 0, then PB is 0 at this point. PB, no pressure of component B. Now when it is maximum, xp is equal to 1, then PB is equal to PB naught, that is this point. xp is maximum, PB naught. Okay. Now if we draw P total versus mole fraction of component B, P total versus mole fraction of component B, then we will get this straight line. Okay, P total is PA plus PB. Now again we know that P total is PA naught in terms of XP, so PB naught minus PA naught XP. So it is y is equal to mx plus c. So it is a straight line again. So y is equal to mx plus c. So mx plus c. So xb is equal to, jodi xb is equal to minimum value, when it is xb is minimum, when xb is minimum, then value is 0. So when xb is 0, P total is P A naught, that is the minimum value of P total is P A naught, minimum value. When xb is maximum, 1, that is no A, component A is present, then xb is maximum, then value of total pressure is PB naught. So value of total pressure, minimum value is PA naught, maximum value is PB naught. So here you can see that the value of PB naught, A.2 higher than PA naught. That means the partial vapor pressure of the pure component B is greater than partial pressure of the pure component A. From this we can say component B is more volatile than component A. So we can conclude that as partial vapor pressure of B is greater than A, so B is more volatile than A. And observation, when we plot, already I explain koilu PA versus PB, আমি কি পাম, straight line পাম. Similarly P total versus XP koilu আমি এটা straight line or linear plot পাম. Okay, so graphically we can explain this Raoult's law in liquid solution. Next topic is next one, the composition of vapor phase. So etia ami liquid solution or composition XA XB consider kori. So these are the composition of component A and B in liquid phase. Now if Y and YB are the mole fraction or composition of component A and B in vapor phase, then we can say, ami etu first year paisu na. So mole fraction of component A in vapor phase, if we represent it by YA, is equal to vapor pressure, partial vapor pressure of component A divided by total pressure, because it is a two component system, so PA plus PB, so PA divided by P total. Similarly YB is equal to PB by P total, so we can ultimately write PA, directly we can write PA is equal to YA P total, PB is equal to YB P total. Now YA and YB are the composition of component A and B in their vapor phase. So in general we can write PI is equal to YI P total, that is vapor pressure of component I is equal to mole fraction of component I into P total. Okay, mole fraction in vapor phase, Y represent mole fraction in vapor phase, remember. So using all this relation we can try to solve this problem. Here it is given that vapor pressure of pure liquid A and B 450 and 700 mm, and you have to find out the composition in liquid mixture, that is XA plus XB. Total vapor pressure is given, it is 600 mm, and also we have to find the composition in vapor phase, that is YA YB. So value of pressure 450 A and B 450 and 700, that is PA naught 450, PB naught 700. Total P total is given. You have to find XA, XB, YA, YB. So given PA naught 450, PB naught 700 mm, P total given 600 mm. We have to find out XA, XB, YA, YB. Okay, now using this relation P total, PA naught plus PB naught minus PA naught XB, put the value. P total is 600, PA naught 450, so PB naught 700 minus 450 XB, so value of XB, it is 0.6. So mole fraction of B is 0.6. Okay, so next XA is 1 minus XB. So XA we can find out direct using this formula, 1 minus XB, because XA plus XB is 1. So it is 0.4. Similarly, if YA and YB are the mole fraction of A and B in vapor phase, so we can find out Y and YB using the formula PA is equal to YA P total, PB is equal to YB P total. Before that, we have to find out PA and PB. Again, we know that according to Raoult's law, PA is equal to PA naught XA. Putting the value, PA naught 450 into XA 0.4, so 180 mm. PB is equal to PB naught XB, PB naught 700 into XB is 0.6, so 420 mm. So using the relation PA is equal to YA P total, so YA is the mole fraction of component A in vapor phase, is equal to PA by P total. PA value is 180 by 600, so it is 0.3. So composition of component A in vapor phase is 0.3. So its composition of component B in vapor phase YB is equal to 1 minus YA. So 1 minus 0.3, so it is 0.7. Or if you want to find out YB separately, then enake ami separately koribo paro. But this is more easier. We need to do this part. Jodi koribo khoja koribo para enake, nohole direct ami easily enake koribo paro. Simple way, because mole fraction is 1. For practice, you can try this one, 2.5 textbook solve problem. You have to try koriba. Mass is given, you have to find out number of moles, tarpor I to calculate koribo para. Raoult's law as a special case of Henry's law. Next topic. So according to Raoult's law, the vapor pressure of volatile component in given solution is given by P1 minus, it is component 1 x1 P1 naught. So ami Raoult's law pora paisu je component A vapor pressure is equal to pure vapor pressure of component 1 into mole fraction of component 1. Okay. Now if one of the component is so volatile that it exists as gas, that is one of the component, if it is gas, then we can apply Henry's law. And according to Henry's law, partial pressure is equal to kH into X. Now if we compare these two equation, Raoult's law, Henry's law, then partial pressure is directly proportional to mole fraction of the solid. Partial pressure is directly proportional to mole fraction of the solid. So we can say that Raoult's law is a special case of Henry's law. Only the proportionality constants are different. Here proportionality constant is P1 naught, that is the vapor pressure of component A in pure form, and here it is the Henry's law constant. So we can say Raoult's law as a special case of Henry's law, in which KH becomes equal to P1. Now vapor pressure of solution of solids in liquid. So vapor pressure of solution of solids and liquid, you can see from this picture. So picture 1, it is a pure solvent in a closed vessel. Here a solution, when we dissolve a non-volatile solute to the solvent, and it is again a closed one. Now you see that in pure solvent, the surface is covered by the solvent molecule only. Now, when we dissolve a non-volatile solute to the pure solvent, the surface is covered not only by the pure solvent, it is also occupied by this non-volatile solute. As the solute is non-volatile, so its escaping tendency is nil. So we can compare, if we compare this to when we dissolve this non-volatile solute to the volatile solvent, the surface is covered by both the solvent and solute molecules. Therefore, the fraction of the surface covered by the solvent molecules reduce. So the number of solvent molecules escaping tendency from the surface in the solution decreases. So we can say that the vapor pressure of the pure solvent is higher than the vapor pressure of the solution. Okay, তার মানে যেটি আমি পিওর সলভেন্ট কনসিডার করিম তো অকুপাইড বাই দ্য সার্ফেস ইজ কভার্ড বাই দ্য পিওর সলভেন্ট অনলি, সো ইয়ার পৰা এস্কেপ কৰিব। নাও ইফ ইট ইজ when we dissolve a non-volatile solute to this solvent, solutor escaping tendency is nil. So as the surface is covered by both solute and the non-volatile solute and solvent, so as the surface is covered by solute and solvent both, so tendency to escape from the surface, solvent molecule or escaping tendency decrease hobo. And in the solution, the vapor pressure of the solution is due to only the solvent molecules, because solute is non-volatile. So vapor pressure of the solution is due to the contribution of vapor pressure of the solvent, not due to solute molecule. So we can say that if a non-volatile solute is added to a solvent, the vapor pressure of the solution is solely from the solvent alone, because solute is non-volatile. This vapor pressure of the solution at a given temperature is found to be less than the vapor pressure of the pure solvent at the same temperature. So pure solvent ke solution or vapor pressure to less hobo, okay, because escaping tendency decrease hobo, just because the solute is non-volatile. The decrease in vapor pressure of the solvent depend on the quantity of the non-volatile solute present in the solution, irrespective of its nature. So this part is very important. So this decrease in vapor pressure, so when we dissolve a non-volatile solute to a volatile solvent, the decrease in vapor pressure to decrease, why? Because surface is covered by the solute molecules as well as the solvent, so solvent or escaping tendency decreases, as a result of which vapor pressure decreases. And this decrease in vapor pressure is depend on the amount of the non-volatile solute present, irrespective of its nature upor depend nokore. This decrease in vapor pressure, for example, if we dissolve 1 mole sucrose to 1 kg of water and 1 mole urea in 1 kg of water at the same temperature, so decrease in vapor pressure will be same. So sucrose 1 mole dissolve korisu, 1 mole urea, two different components but they reduce the vapor pressure in equal extent, okay, because this decrease in vapor pressure depend on the quantity, 1 mole present, same quantity is present, not on their nature, okay. And A2 partor por ami extend korim, so this part is very important. Ami solute molecules to keneke loisu, urea and sucrose, so they will not undergo any association or dissociation in water. So sucrose sugar water or dissolve korile aru urea water or dissolve korile solution hobo, okay. Association or dissociation, ionization type or no hoy. So this type of solute, when same amount is dissolved, what type of solute? That does not undergo any association or dissociation. When dissolved in same amount of that type of particular solute, which does not undergo any association or dissociation in the same quantity of solvent at a given temperature, then their tendency to reduce the vapor pressure will be same, okay. So next, Raoult's law for a solution containing a non-volatile solute and volatile solvent. It states that relative lowering of vapor pressure is equal to the mole fraction of the solute which is non-volatile. So Raoult's law याद की question, when we dissolve a non-volatile solute to a volatile solvent. So non-volatile solute when we dissolve, then vapor pressure reduce. This reduce in vapor pressure or relative lowering of vapor pressure is equal to mole fraction of the solute which is non-volatile. Now relative lowering of vapor pressure, what is lowering of vapor pressure is relative lowering of vapor pressure is equal to mole fraction. Okay, relative lowering of vapor pressure ki hoy moi explain kori aso. So if a non-volatile solute, suppose B is dissolved in a volatile solvent A, and P is the total pressure of the solution, P to total pressure of the solution consider kori. So PA is the vapor pressure of the solvent and PB is the vapor pressure of the solute. So PA and PB are the vapor pressure. PA is the vapor pressure of the solvent when we dissolve a non-volatile solute to it, and PB is the vapor pressure of the solute in solution. So mathematically we can write P is equal to PA plus PB. Okay. So PB, it is the vapor pressure of the solute. So as the solute is non-volatile, so its contribution towards this vapor pressure is A2 contribution ki hobo nil, PB is nil. So PA is equal to PA naught as B is non-volatile. Now PA, what is PA? PA is PA naught into XA from Raoult's law. Okay. So we can write, if we replace XA by XB, so P is equal to PA naught 1 minus XB. So 1 minus XB, so we can write it PA naught minus PA naught into XB. So A2 jodi ami left side change koru aru A2 ami right side anilu. So PA naught XB is equal to PA naught P. Now P mane ki? P mane PA na, ami already palu P is the total pressure which is equal to PA plus PB. Now PB is nil, so P is equal to PA. So PA naught, it is the vapor pressure of the component, pure component A, jetia component A before mixing component A okole asile, tar pisot minus P, P means PA buliyo kobo paru ami, that is the vapor pressure of the component A in solution. Now in solution vapor pressure decreases, so PA naught minus P is known as the lowering of vapor pressure. So when we dissolve a non-volatile solute to a volatile solvent, then this lowering of vapor pressure is shown by this PA naught minus P, or sometime you can write PA naught minus PA, because PA aru P total to same hobo no. So PA naught minus P, that is lowering of vapor pressure, divided by PA naught, this term is known as relative lowering of vapor pressure, which is equal to the mole fraction of the solute which is non-volatile. So we can say that relative lowering of vapor pressure is equal to mole fraction of the solute. Okay, thank you. So next class আমি ডিসকাস করিম colligative